at this. Hey, as you can see, I'm actually Look at this. Hey, as you can see, I'm actually balancing this heavy hammer on my fingertip, and actually really is talking about the concept of a centroid, which is that one point, basically that balance point where an object will just totally balance perfectly. So the centroid of this is kind of located where my finger is, which is kind of cool. Complicated and difficult to find in general. If you want to find the centroid of a really crazy weird shape like a hammer, you know what you got to use? You got to use calculus. That's right. But for triangles, it's actually much easier. Let's have a look. So what I want us to do is to use the centroid theorem to find the various lengths, given that with this triangle, GL equals 12 and HM equals 10.2. So what's the centroid theorem say? Well, first of all, how do you find the centroid? Well, that's the point you get, whereas if you were to bisect each side through the vertex opposite, so take this point and then now draw a line that bisects this side, so you get X, draw a line that bisects this side and passes through B, so you get this Y, and similarly here, go through C and find the midpoint here and you get Z. Well, first of all, it's an amazing fact that each of those three line segments will actually meet at one point. That's not at all obvious, and that point is called the centroid, and that actually is the balance point. So if you were to take a triangle and balance it right there, you'll be able to balance it perfectly like on the head of a pin. Now, here's what the centroid theorem says, which is so cool and so not obvious, that if you look at the entire length here, AX, and you look at the length from A to P, so from the vertex to that centroid point, it turns out that the theorem is that this length will equal 2/3 this length. How cool is this? That means that this is 2/3 the way all the way here. And the same thing is true here. This is 2/3 of the way to the whole distance. This is 2/3 of the way to the whole distance, which, by the way, means that this little piece left over from the centroid to that midpoint, well, since this whole thing is one whole thing and this is 2/3 of the way, this must be 1/3 of the way. Since this is 2/3 of the way here, this must be 1/3 of the way, and so forth. So you can actually do some really cool things with this, as now we're going to see. So take a look at this figure, and we see that, in fact, P is the centroid because I've bisected each of the sides and then took that point of bisection, that midpoint, and connected it with the opposite vertex. So we go here to here, we go here to here, we go here to here, and we see, of course, that they all coincide at P. And we're told a couple things here. We're told that GL equals 12. So where is G? GL. So this entire thing, whoops, this entire thing, I'm going to draw it right now for you. You're going to see it for yourself. This entire thing is, in fact, 12. And that is 12. And I'm also told that HM, where is that? HM, that's this entire thing. And I don't want to draw it in here. I don't want to get too complicated. I'll draw it in a little bit. This entire thing right here is 10.2. Okay, so the first challenge that I want us to consider is to see if we can figure out what is the length of GP. Well, where's GP? Well, GP is right here. And we see that is from the vertex to the centroid point. So we know by the centroid theorem that's going to be 2/3 of the way of this whole distance. And the whole distance is, in fact, 12. So we see that GP is going to equal 2/3 times the entire length, which is GL, which is 2/3 times 12. And that, of course, is 8. And so this length right here is 8. See how easy this is? Let's try another one just for fun. How about let's find the length PM. So where's PM? Well, PM, notice, is over here. It's not from a vertex to the centroid.